Hey, ladies and gents. We are nearing the end here. Only a couple more topics to go. Yay! A couple things quick. If you hear screaming in the background, I swear everything is okay at my house. My son is just adamantly refusing to nap. He's fine. He's safe. He's in his pack and play. If you hear doors slamming, my daughter and husband are outside and will probably come running in and out of the door, mainly the 5-year-old, not my husband. It has been one heck of a day here at Mrs. Peterson's house. So, we're just going to go with it. And excuse me if I make a million and seven mistakes as we go through these notes. But as we talked about in our live Google Meet, or I'm actually recording this before our Google Meet. So, what I intend to talk about, hopefully, we covered in our Google Meet, is what it means to be continuous, just generally. What does it mean to be continuous? So, today in this set of notes, we're going to talk about the formal definition of continuity, the formal definition of what it means to be continuous, because this is going to carry on into calculus, of course, for those of you going on to calculus, whether in college or next year in BC. So, why is this definition of continuity important? And for those of you who are going on to BC, it will probably show up at least once, if not multiple times, in the AP test. It is a necessary condition to be established for differentiation and integration in calculus. And what those mean, you'll get into for those of you who've never heard that before. So it's an important condition to establish in order for you to continue on with other aspects of calculus. So notes are linked up, a blank copy of the notes are linked up on a Canvas if you want to follow along with your own copy of notes, otherwise with notebook paper. And otherwise, I am going to switch this camera around and we will get started here. Okay, so the formal definition of continuity, what does it mean for a function to be considered continuous? Has three parts, as you can see. All three parts must be true in order for a function to be continuous. It is not enough to say, hey, my function met part 1, or it met parts 2 and 3, or 1 and 3, or whatnot. It must meet all parts in order for a function to be continuous. So in order for a function to be continuous, first thing, f of c is defined. So in other words, if I ask you to determine the continuity of a function at a certain point, that point, like if I ask you, tell me about the continuity of the function at the x value of 4, f of 4 has to be defined. I can't have, I must have an actual point on the graph. And of course, we will go through what all this means in some application of math problems here coming up. So part 2, the limit of the function as you approach the x value in question must exist. Not only must the function be defined, the limit must exist as well. Keep in mind, when we first started talking about limits, we said the value of the limit and the value of the function, one means nothing about the other, one does not influence the other. That is still true. But in order to be continuous, the function needs to be defined and the limit needs to exist. And the third condition that must be satisfied in order for a function to be considered continuous, or in order to be continuous at a certain point, is the value of the function and the limit of the function must be equal. And again, all three of these things must be held true at the same time in order for a function, or in order for a certain x value within a function to be considered continuous. So the rest of the stuff we will come back to. This is a really good reference sheet right here, what all these things mean. But let's talk about this definition of continuity. So rather than talking about this entire function right now and its continuity as a whole, well, actually, let's do it. This entire function, if I look at it from left to right in its entirety, not continuous. Easiest way to determine that is, can you trace the function from left side start to the right side end, start to end, without picking up your pen? And obviously I can't, because as soon as I get here, I have a jump. I have to pick up my pen in order to get down here. There's a little screaming in the background if you can hear it. So sometimes in calculus, though, it's necessary to not just look at the continuity of the function as a whole, but look at continuity at certain x values. So first, we are going to look at the x value of -1, which is right here. I will do these in different colors. So are we continuous at -1 at that particular x value? Well, the best way to determine that is to run through the three conditions for continuity. So condition 1 says f of c, in this case, we're looking at -1, must be defined. So I'm going to look at -1. Is there a defined point? The answer is yeah. Right there, there's a defined point at a y value of 3. So we pass condition number 1. Condition number 2 says the limit of my function as you approach that x value, so -1, has to exist. So I am going to go here, and the limit, I'm going to find it graphically, obviously, because we have a graph. I'm going to approach from either side, and notice where my finger and my pen are, 2 different places. So does the limit exist? No, the limit does not exist. So at -1, we are not continuous because we fail condition number 2. We fail condition number 2. Now, there are a multitude of different types of discontinuities. Discontinuities meaning the aspects or parts of the graph that are not continuous. There are different types of discontinuities that could occur. We could have holes. We could have jumps. We can have asymptotes. So I'm going to come back up here and we're going to talk about classifying discontinuities. Holes go in one category, and jumps and asymptotes go in another. So what's the difference? Well, all 3 are obviously different, but what is the difference and why are they in 2 different categories? We call holes removable discontinuities. So holes are a removable discontinuity. And jumps and asymptotes are non-removable discontinuities. And in the long run, these removable discontinuities can be overlooked, if you will. There are ways around them. Non-removable, a little bit more difficult. So what does it mean to be removable versus non-removable? Easiest way to describe it is a removable discontinuity can be fixed, if you will, fixed meaning be made continuous by moving or adding one point. Can be fixed, or can be, and by fixed I mean made continuous, can be made continuous by adding or moving one point, exactly one point, not many. So normally on my whiteboard, I do this demonstration with a magnet and moving a magnet as a point to see if you can fix what's going on. Unfortunately, I don't have something small enough to put on this graph to look like one of those little magnets, but taking a look at this discontinuity at -1, we know we're discontinuous because we do not have a limit, does not exist, approaching 2 different places. Can I fix? Can I make this continuous by adding 1 point? Well, if I fill in this point right here, that'd be adding 1 point. I actually no longer have a function, and I have this big gap right here. What's happening right now is a jump. Now, obviously, jumps we already put in the non-removable discontinuity category, meaning it cannot be fixed. I guess I could add that on here. Cannot be fixed by adding or moving 1 point. Cannot be fixed. Again, fixed means being made continuous by adding or moving a point. So now some people say, well, down there at -1, if you could just imagine picking up this graph, I could pick it up and just slide it down here. And I'm just moving that point from here to here, and all of a sudden we're continuous. Well, think about that. That would be great in theory. But if I were to be able to pick up this portion of the graph and just drag it down to connect here, I've actually moved far more than 1 point. I've moved the entire graph. So if I am going to classify this discontinuity at -1, this discontinuity, which is a jump is when you have that big gap in there. Yes, there's a hole here too, but the biggest issue is that I have this ginormous gap. So it is a jump, which is non-removable. And just because I don't have a lot of room, I'm going to abbreviate here. So I will write out all of the answers for B and C in my answer key, but I'm only going to go through B with you, and then I will let you all try C on your own. You can verify it with my answer key. So is the function continuous at Actually, you know what? I'm going to do C. I'm going to let you do B. I'm going to do C, just glancing at the graph. Is the function continuous at 1? Well, I'm going to find 1. I'm doing pink right here. Move this over so my little... Okay, so first condition of continuity. Condition 1 is that f of, in this case, 1 exists. So I'm going to go to 1, look for a filled in circle. Yes, I got it. It is at 2. We pass condition 1. Good to go. Condition 2 says the limit of my function as we approach, in this case, 1 must exist. So I am going to use 2 pens here. I'm going to find 1. I'm going to jump on the graph on either side. I'm going to approach 1 and notice where my pens are as we squeeze 1. They're in the same location, which is a location of a y value of 1. Yes, my limit exists. We say the limit is 1. We have passed the second condition of continuity. Well, the third condition of continuity says f of 1, which is 2, has to equal the limit as we approach 1 of the function, which happens to be 1. So in other words, is 2 equal to 1? Obviously, that is false. We are not continuous. This function is not considered continuous at 1 because we failed, although we passed 1 and 2, we failed part 3. So taking the next step, classifying the discontinuity. So we're going to look at what's happening here. Is this a hole? Is this a jump? Or is this an asymptote? This is not obviously an asymptote. This is not considered a jump. It is not the same thing that's happening here. We don't have a big gap in our graph to get from one side of the graph to the other. Our issue just is that we have a hole. We have a hole which is considered removable if we're going to classify it removable. So again, removable means I can fix it by adding or moving 1 point. If I just added a point right here, I wouldn't want to do that because then I'd fail the vertical line test. I wouldn't have a function. We want to focus in function land. But I could move this point. If I could pick up this point right here and just drop it right here, this graph would be magically made continuous because that defined point would get moved to where the hole in the graph happens to be. So again, I'm going to let you try B. If you want to pause the video, go check the answer key, you totally can. And we are going to talk about some continuity of functions without looking at a graph. Okay, so here we go. You know what? We'll run through a couple more discontinuities. Again, I'm not going to do every aspect of every single problem. Anything I don't do will be on the answer key, which is on Canvas. So for this graph, we're going to identify any discontinuity and explain how the definition of continuity is not satisfied, classifying that discontinuity. Well, looking at this graph, I am going to, again, discontinuous as in a whole is anywhere I'd have to pick up my pencil in order to continue drawing this graph. So if I trace, I would have to pick up here. I have a discontinuity, or I am discontinuous US at an x value of -2. At -2, I'd have to pick up my pen in order to keep tracing. So we'll get back to classifying that one and explaining how it doesn't satisfy the definition of continuity. Keep tracing. I just heard a big thump upstairs. I promise my son is not big enough to climb out of his pack and play. Told you, it's been a day over here. Yeah, I have a defined point there. That's just part of the graph. I'm good. Trace. I'm going to have an issue right here at an x value of 3. So we are discontinuous at -2. We are discontinuous at +3. And if I keep tracing, I'm good. So I'm going to do one of these. I'll let you check the other. I'm going to go with -2. So I am going to focus on -2. I'll let you deal with x equals 3. I'm going to explain how the definition of continuity is not satisfied. So part 1 says f of -2 has to be defined. Well, f of -2, oh, right there's my filled in point is 2. We're good to go. Part 2 says the limit as we approach -2 for this function has to exist. While hopping on this graph on either side, similar case to what we had before, does not exist because I am in two different places. We failed the definition of continuity because our limit does not exist. Classifying that discontinuity, we can tell right here I have a huge gap, so we have a jump, which is non-removable. That cannot easily be fixed, if you will. Non-removable. I'll let you run through 3. So graphs are pretty easy to determine, are they continuous or not? But we need to be able to do this without a graph and without the aid of a graphing calculator. So here we go. Let's talk about functions. Well, we know there are groups of functions we're pretty familiar with, different types of polynomials, rational functions, square root functions, absolute value functions, and whatnot. Rational functions, these fractional functions, are ones that we know there could be issues at. Rational functions, as you learned in Algebra 2, could have holes, they could have asymptotes. So how do you determine that? If you remember back to Algebra 2, for a rational function, holes and asymptotes are really largely determined once you factor your numerator and denominator and identify if any of those factors can cancel. So I am going to factor my numerator by GCF. I am going to remove a GCF of 2, leaving me with 2x plus 5. And I am going to factor my denominator using AC or X method. And I need 2 factors that multiply to negative 15 and add to negative 2. And that is going to be negative 5 and 3. I don't have a coefficient of x squared. So I go right into factored form, x minus 5 and x plus 3. So in order for me to have a hole, as we actually learned when we were finding limits analytically, a hole is when you have a factor that cancels in both the numerator and denominator. Obviously, we don't have that. These are the most similar factors, but they are not identical. They don't cancel, meaning this rational function has absolutely no holes. We also know, though, that rational functions cannot have a denominator equal to 0. So we are going to take a look at this and look at where could the denominator equal 0. So our denominator equals 0 at x equals 5 and x equals negative 3. Anytime the denominator equals 0 but does not cancel a factor in the numerator, that means we have a vertical asymptote at each of those locations. We have vertical asymptotes at x equals 5 and x equals negative 3. Now, discussing this continuity, we can say obviously we are not continuous, and these are because they are asymptotes. Asymptotes fall in the category of non-removable discontinuities. I really hope you can hear the screaming, only because it's funny to me as a mom. Like I said, I swear he's fine. Non-removable discontinuity. Discontinuities. I am not a speller. Really have to sound that out. Any rational function, I would expect that you can determine if it has asymptotes or holes. You've been doing that for Algebra 2. We know, so there's 2 of our discontinuities, holes and asymptotes. So then the next question is, jumps. Where do jumps occur? Well, there are other functions that can naturally create jumps, but I think I mentioned this before. Jumps most naturally occur potentially in piecewise functions. I hope y'all love yourself some piecewise functions. So let's talk about continuity. Where could a piecewise function potentially be discontinuous? Well, I need to look in 2 places. We need to look, one, within each piece of the function first. So I'm going to look in this one. The first piece, 2x minus 1, is a line. I'm going to ask myself, are lines, do they have the potential to be discontinuous? The answer is no. Lines are always continuous by themselves. 3x plus 1, continuous by itself. Similarly, if I check over here, I'm going to look at each function and I'm going to ask myself, could that function have any discontinuities? If it does, I need to identify it and see if it is within the range for that particular piece of the piecewise function. If it is within that range, then yes, it's a discontinuity. If it is not within that range, then I don't have to worry about it because that function would not be graphed at that location anyway. So going back to B, both of these pieces are lines, no discontinuities. So the only place that I might have a discontinuity and a place that I might have a jump is right here where one function ends. This line is only graphed for x values less than 1, and the other one begins. This line is graphed for x values greater than 1. I need to determine at 1, am I continuous or not, because that ultimately would determine if this function is continuous in its entirety. So how do I determine if I'm continuous at 1? I'm going to run through the definition of continuity. So part 1 for the definition of continuity, does g of 1 exist? Well, you have learned how to evaluate piecewise functions. In order for me to find g of 1, I'm going to look for which inequality 1 satisfies. 1 is not greater than 1, but 1 is less than or equal to, right there, 1. So that means I'm going to plug the 1 into this piece. So 2 times 1 is 2, minus 1 is 1, g of 1 is 1, bingo, we're good. So the second piece is, does the limit as we approach 1 for g of x exist? Which brings us to, how the heck do you find the limit when it comes to a piecewise function? Again, I alluded to this earlier when we had talked about limits in a previous video. Piecewise functions are coming for you. So it's a really big question. How the heck do you find the limit in a piecewise function, especially when you're looking for the limit at the point where one function ends and the other one begins? If I asked you to find the limit at, let's say, 4, no issue. 4 fits in this second piece, direct substitution. 12 plus 1 is 13. The limit as you approach 4, 13. But when I'm talking about the limit at the point where one function ends and the other function begins, then we are going to have to take this somewhere else. We're going to need another piece of information. So quite honest, I hope this video isn't getting too long yet. I will check here shortly. I wish I had a running timer on here. I am going to jump right here back to the front page. We're going to talk about one-sided limits. For different aspects of continuity and for piecewise functions, you need to be able to identify one-sided limits. The limit from the left, hence the left hand, and the limit as you approach from the right-hand side. Right hand. Okay, so what does the notation for a one-sided limit look like? Well, it's going to look pretty familiar. I'm going to use just the general function f of x as we approach a generic constant value. And the limit, notice nothing looks different yet, right? Other than I'm just using generic letters. Okay, so what does the notation for a left-handed limit look like? What does the notation for a right-handed limit look like? And then we'll talk about what does that actually look like in practice. Well, ready? Right now it looks like general limit notation. The limit as you approach from the left, all you're going to see is this tiny minus sign up by the constant you're approaching. And that minus means from values less than that value, x value in question. So that minus sign means a limit as you approach from the left. And a little plus sign up there means as you approach from the right or from values greater than that constant. Now, something to note. A plus sign does not mean you have to approach from positive values. Similarly, a minus sign does not mean you have to approach from negative values. It just means you have to approach from values less than the value in question or greater than the value in question. Okay, so what does this look like? We're actually going to go the harder route first. We are going to go the route of looking at the direct equation first, and then we'll go back to the graphical one-sided limits later on. Okay, so what about the limit as we approach 1? Okay, I can't just do direct substitution at 1 because 1, again, is our breaking point. So in order for me to find the limit at 1, it's all summarized right here. The limit at 1 exists and is, can be found if the limit as you approach from the right is the same as the limit as you approach from the left. So if the left and the right-handed limit both exist and they are the same, then we have found the limit at 1. So in other words, in order for me to find the limit at 1 for this function, I can't just, again, plug in at 1 because it's a breaking point. So I'm going to find first the limit as we approach 1 from the left. Well, how do I do that? Well, I'm going to approach 1 from the left, so I'm going to look at which piece shows values less than 1 or values to the left of 1. That's going to be this piece, this top piece right here. I'm just putting the minus for the left-handed limit because literally it says values less than or equal to, in this case, 1. Okay, so I'm going to ignore this bottom piece. How do we find a limit? Well, we find a limit. Our first try is direct substitution. So as I approach 1 from values less than it from the left, I'm going to try direct substitution. 2 times 1 is 2, minus 1 is 1. The limit as we approach from the left is 1. Now we're going to go through and we're going to find the limit as we approach 1 from the right for this function. Okay, well, values to the right are values greater than 1, which is the second half here. And so I'm only going to focus there. How do we find a limit analytically? Direct substitution. I'm going to directly substitute into this piece and this piece only. 3 times 1 is 3, plus 1 is 4. The limit as we approach 1 from the right is 4. Well, in order for the limit at 1, again, left-handed limit, right-handed limit are not the limit. It's just helping us find the limit. In order for L, the limit, to exist, the left and the right-handed limit must be the same. Just thought of this. I have no idea why they put the left-handed limit notation on the right and the right-handed limit notation on the left. This was actually a picture directly from your book, I think, or I took it online. I'm not sure. Somebody else's textbook, but that's a textbook picture. Just kind of odd that happened. Anyway, back to here. The limit from the left is 1. The limit from the right is 4. Does 1 equal 4? No, 1 does not equal 4, which means the limit as you approach 1, because the left and right-handed limit are not the same, the limit at 1 is D N E. It does not exist. I will show you in a picture what is actually happening later. So back to what we were trying to do in B, discuss the continuity. Is this function continuous? Well, piece 1 is continuous because it's linear. Piece 2 is continuous because it's linear. But when I put these pieces together, focusing on their breaking point, is it continuous? The answer is no, because we fail part 2 of the definition of continuity. Not continuous at x equals 1. So what is happening at 1? Well, if I kind of think about what our numbers told us, I have, as I approach 1 from the left, I have a point of 1. I plugged in 1, 1, 1. As I approach 1 from the right, I have a point that's not defined really because there's no equal sign, but I have a 0.14. Ultimately, as I approach from the left, let's see, this is not a perfect picture, but as I approach from the left, I have something to this extent of, I have the 0.11, and as I approach from the right, we had something to this extent, we had 1, 4. So if you look at that little picture right here, we can tell that we have a jump, which is a non-removable discontinuity. Okay, so I'm going to let you try see if you can discuss the continuity of that function, which is going to mean you're going to have to find some one-sided limits. I think that is most likely otherwise enough new material for today. I probably need to go take care of the screaming child upstairs. But quickly, what I want to refresh, if you need to see it, you can keep watching, otherwise you can stop the video. But how do I graph a piecewise function in my calculator? If you want to stay on to have a refresher as to how do I graph a piecewise function in my calculator, do so. If not, you're going to have one more question pop up in this video for you to answer before you are done till next time. So calculator. I am actually going to graph the piecewise function from B, the one that we just talked about the continuity about. I'm going to graph this one in my calculator. So how do I do that? In my Y1, we had said put everything in Y1. You don't want to put each piece. The piecewise function in B had two pieces. I don't want to put one piece in Y1 and one in Y2 because it won't factor in that inequality where one ends and the other begins. I'm going to put everything in Y1 and I'm going to put every aspect of each piece in its own parenthesis. So we have 2x minus 1. So the function part is in its own parenthesis. And then our inequality, x is less than or equal to 1, is in its own parenthesis. The less than or equal to is under second math, which is test. We wanted less than or equal to 1. So there's the first piece of my piecewise function. And then I'm going to add on the second piece. Now, if you decide to try part C in the calculator, you have 3 pieces. So you're going to add on each new piece. I mean, you could have a million pieces of a piecewise function if you wanted to. So our second piece, and again, using parentheses, is 3x plus 1. And then in its own set of parentheses, the inequality, x is second test, second math, greater than 1. And I now have put in our y equals the piecewise function. I'm going to hit zoom 6 just because I don't know what my window's at. That's the standard viewing window. And you will notice right there, you can see that jump that I kind of sketched out on my piece of paper on the notes. There is our piecewise function. And you can easily now see we are not continuous at 1 because we have that non-removable discontinuity of a jump. Okay, I think that's enough. Again, you're going to have, you have a couple questions in this video that you should have answered, and we will pick up where we left off next time, ladies and gents. I will see you later, and I will go get my screaming child. I promise he's okay.